Hello and welcome to Step 3 of the MEDomicsLab testing phase. Today, we'll be preparing our tables for machine learning. This process will be divided into 5 steps. First, we'll reduce our extracted features from Step 2. Second, we'll navigate through the MEDprofiles module to merge all our data into a master table and prepare the MEDprofile figure. Third, we'll visualize our MEDprofiles figure. Fourth, we'll create time points from our figure and export them as CSV tables. Finally, we'll split our time points data into learning and holdout sets. At this point, you should have at least 2 folders containing CSV files in your data folder, one containing the extracted features from Step 2 and another containing the CSV files we provided you at the beginning of Step 2. Well, let's start by reducing our extracted features. This step is necessary because our extracted features are extensive CSV files, and you won't be able to observe all this data simultaneously using the MEDprofiles process. So, go to the Input module and expand the Feature Reduction tool accordion. You have at least 2 options to reduce data: PCA, which is Principal Component Analysis, allowing you to choose the number of principal components to keep by observing the resulting explained variance. The second option is Spearman Correlation, where you can choose which columns to keep based on their correlation with the target column. Here, we are going to apply PCA to the features extracted through a pre-trained model, the notes and the images. Let's start with the images. Select the image extracted features CSV file and allow the app to load the information. This may take a few seconds. Then, choose all the CSV columns except the first 2 columns, which represent the patient identifier and the date. Afterward, click the Compute Eigenvalues button. Here, you can observe the resulting explained variance based on the number of principal components you choose to keep. Select 10 principal components by clicking the corresponding row. Now, let's configure our dataset options. Check the Merge Unselected Columns in the Result Dataset option to retain patient identifiers and dates in the resulting dataset. Set image_reduce.csv as the CSV file name and use image as the column name prefix. Finally, click on the Compute PCA Dataset button. Your dataset will be saved under the Reduced Features folder in your Data directory. Upon inspection, you will notice that it now contains 10 feature columns along with the patient identifiers and date columns, as expected. Let's perform the same procedure with the InDischarge Extracted Features CSV file. After selecting the CSV file, wait for the app to load the data. Next, choose all columns except the first 2. Click the Compute Eigenvalues button, then select 10 principal components. Ensure the Merge Unselected Columns in the Result Dataset option is checked. Set the file name as InDischarge_reduce.csv and use InDischarge as the column name prefix. Finally, review your reduced CSV data to verify that everything is in order. Then, let's do the same with the InRadiology Extracted Features CSV file. After selecting the CSV file, wait for the app to load the data. Next, choose all columns except the first 2. Click the Compute Eigenvalues button, then select 10 principal components. Ensure the Merge Unselected Columns in the Result Dataset option is checked. Set the file name as InRadiology_reduce.csv and use InRadiology as the column name prefix. Here again, review your reduced CSV data to verify that everything is in order. Now, we aim to reduce the event extracted features CSV files using Spearman correlation. To proceed, we need the target column, which is currently not included in the extracted features CSV files. The target associated with each patient is available in the CSV file Selected Patients list that we provided you. We will merge this CSV file with the extracted event features. Close the Feature Reduction tool accordion and open the Merge tool accordion. We'll start with the TS Chart Extracted Features CSV file. Select it as the first dataset. The column to merge on is subject_ID. Keep all the columns as selected columns. Add another dataset to merge on and select the Selected Patients list CSV file. Set the merge type to inner and choose Subject ID and Target as selected columns. Name the resulting file TS_chart_with_target and keep the .csv extension. Your dataset will be saved in the same location as the first dataset, in the Extracted Features folder. If you open it, you should see that the target column has been merged at the end of this file. Let's repeat the process with the MEDomicsLab Extracted Features CSV file. Choose subject_ID as the column to merge on, and keep all the columns selected. Select the selected patients list as the second dataset with an inner merge type and choose subject_ID and target as the selected columns. Name your resulting CSV file TSLab_with_target. Once again, you can check if the merge result meets our expectations. Finally, let's repeat the process with the TS Procedure Extracted Features CSV file. Choose subject_ID as the column to merge on and keep all selected columns. The second dataset is still the selected patients list with the same options. Name your resulting dataset TS Procedure with Target. Now, close the Merge Tool accordion and reopen the Feature Reduction Tool accordion. Choose the Spearmint tab. Let's start by selecting the TS Chart with Target CSV file. Wait for the app to load the information and then select all the columns, excluding the two first columns corresponding to patient identifiers and dates, and the last one, which is the target. Choose the target as the target column and press Compute Correlations. The correlations for the selected columns will be displayed in decreasing order of correlation with the target. Here, choose to keep the top 10 most correlated columns by checking the first 10 associated rows. As dataset options, check the Merge Unselected Columns in the Result Dataset option but not the Keep Target in Dataset option to retain patient identifiers and dates in our result data frame. Set the result CSV file name as TS Chart Reduced and press Compute Spearmint Dataset. Your result dataset will be saved in the Reduced Features folder and should include the top 10 most correlated columns with the target, along with the patient identifiers and dates. Let's repeat the process with the MEDomicsLab with Target CSV file. Wait for the app to load the information. Choose all the columns except the first two, and the last one is the ones for Spearmint correlation. Set Target as the target column and click on Compute Correlations. Pick the top 10 columns most correlated with the target, and keep the data frame options consistent with the previous computation. Name your result file as TSLab Reduced. Finally, let's repeat the process with the TS Procedure with Target CSV file. Choose all the columns, excluding the first two and the last one, for Spearmint correlation. Set Target as the target column. Click on Compute Correlations and select the top 10 rows. Keep the dataset options consistent with the previous settings and name your result file TS Procedure Reduced. Finally, press the Compute Spearmint Dataset button. Well, the first part of this step is done. We have our 6 reduced CSV files for the second part. Now, we are going to merge all our data into a comprehensive master table using the MEDprofiles process. For additional information about MEDprofiles, please refer to our GitBook. So, open the MEDprofiles accordion. This module takes a data folder as an entry to check all the CSV folder formats. It means that all our data have to be in the same folder. Here, we are going to work with the Reduced Features folder, so please copy-paste the demographics embeddings that we gave you at the beginning of Step 2 into this folder to have all the data in the same place. By default, if you don't have any master table yet, the MEDprofiles module will work on the Extracted Features folder. Here, we want to merge our reduced extracted features, so change the data folder to Reduced Features. Then, wait for the app to load the CSV files matching the required formats. Once it's done, select all your CSV files from the Reduced Features folder, the 6 we created in Part 1 of this video, and the demographics. Then press the Create Master Table button. Your master table will be created under the Master Tables folder, under the MEDprofiles folder in your data folder. Then, you may notice that your data folder for the MEDprofiles process has been automatically changed to Master Tables. Now, you can select the master table to continue the MEDprofiles process by pressing the Create MEDClasses button. Your created MED classes will be displayed. You will notice some classes named with the MED prefix. These are the base classes of the MEDprofiles process. If you look at the other classes, you will notice that they are familiar. In fact, They correspond to all the column prefixes we set in Step 2 and in the Feature Reduction tool. The next step is to instantiate our master table data as MEDprofiles using our created Med classes. Simply click on the Instantiate MEDprofiles button. This process may take a few minutes. Let's take a look at our master table while it's running. This CSV file contains all our data merged by patient and date time. In fact, it is a substantial file, primarily longitudinal, containing a lot of NaN values. When the process is complete, you will find that you have all the necessary data to visualize the MEDprofiles figure, the Med classes folder, and the MEDprofiles binary file. These are located in your MEDprofiles folder, which was created the first time you open the input module. Begin by clicking on the Open MEDprofiles Viewer button. The figure will take a moment to load. Well, here you will see a lot of information on the figure and several options displayed at the right. In order to fully understand what you can do with the figure, I recommend you take a look at our documentation and video tutorials about MEDprofiles. The original figure displays all the patient data on axes representing classes and dates. Each patient has a unique color, but when there are many patients, the colors become harder to distinguish. Let's explore the figure a bit. For instance, we can observe each patient. Click on the Separate Vertically button, which will separate all the patients currently overlaid on the class's axis. Then, you'll be able to zoom in on both axes until you find a set of points of the same color. You'll realize that this small set of points in this vast figure actually represents all the data for one patient. Well, you may observe each patient independently, figuring out what the data looks like, and take time to observe the figure. Press the Restore button on the figure to retrieve the original view. Here we are going to define 4 time points. To set our time points properly, we are going to set the time relative to the end-discharge class. This will allow us to align all patient data with the time of their first discharge. So, select end-discharge as the relative class and press Set. Next, we are going to set our time points through horizontal selection in the figure. So, click the horizontal selection button directly in the figure and define the first time point. For this one, we are going to select all the data that happened before the first discharge node, which is time point 0. Once the selection is done, press the Set T1 button. Next, we are going to set approximately 140 days for time point 2 and the same for time point 3. To do this, simply take your horizontal selection, move it right after time 0, and reduce it to approximately 140 days. Then, select 2 as the time point and press Set T2. For time point 3, drop your horizontal selection right after the T2 area. Select 3 as the time point and press Set T3. For the last time point, drop your horizontal selection at the end of the time point 3 area. Ensure it covers all the last points, select 4 as the time point, and press Set T4. Now that we have defined our time points, it's time to export them as CSV files. As we want to have at most 1 line per patient in our learning tables, we are going to check the option Merge Time Points by Patient and set the merging method to mean. This will export 1 line per patient that contains the mean of all the patient data in the time point area for each attribute. Finally, press Export Time Points to CSV. Your CSV files will be saved under the folder Time Points in the MEDprofiles folder. Feel free to observe them. See how many patients each of them contains, if all of them contains the same number of attributes, and if they contains NaN values. Now, let's move on to the last part of this step 3, the creation of learning and holdout sets. Our goal is to divide our patients into 2 groups, and we want to apply this split consistently across all the time point CSV files. The challenge is to ensure that a patient is either in the holdout set or in the learning set for all the time point CSVs. To achieve this, we'll utilize the patient list. We'll split it into learning and holdout sets using the holdout set creation tool. Subsequently, we'll use these split lists to separate our learning and holdout patients in each time point CSV file through the Merge tool. Now, let's open the holdout set creation tool accordion. Select the selected patient list from the CSV files we provided you as the dataset from which we want to create the holdout set. Check the Shuffle and Stratify options and select Target as the column to stratify on. This will ensure that the two datasets have the same proportion of deceased patients. Leave the other options as default. 20% for the holdout set size, drop as the NaN method, and set the holdout set name as Patient List Holdout, letting the CSV extension. Then, press the Create Holdout Set button. Your two sets will be created under the same folder as the selected patient list CSV file. If you open the two generated CSV files, you will observe that the learning file contains 80% of the patients, equivalent to 160 patients, and the other contains 20% of the patients, equivalent to 40 patients. You can also observe that the proportion of each target has been preserved. Now, close the Holdout Set Creation tool accordion and open the Merge tool accordion. We are going to create 8 datasets, 2 per time point. Here, I noticed that the column names for subject ID are not the same in the time point CSV files as the ones in the selected patient list. So, I just renamed all the ID columns in all the time point CSV files to subject_ID. If you have to do that too, don't forget to save your datasets after updating the column names. So, let's go back to the Merge tool. We are going to start with time point 1. Select T1 as the first dataset. Choose subject_ID as the column to merge on. Keep all the other columns selected. Choose Holdout Selected Patient List as the second dataset, with inner as the merge type, and select subject_ID and target columns as columns to merge in the result dataset. Let's name this dataset T1_holdout and keep the CSV extension. Press the Merge button. Let's do the same with T1 and the Learning Selected Patient List CSV file, using all the same options. Name this file T1_learning. Then, let's do the same with T2 and the Learning Patient List, using the same options. Name this file T2_learning. Do the same for T2 and Holdout Patient List. Again for T3 and Holdout Patient List. Now for T3 and Learning Patient List. Then for T4 and Learning Patient List. And finally for T4 and Holdout Patient List. Well, now you can check your CSV files. Ensure that all the learning and holdout time point files have the target column. To be certain that you merge the learning and holdout sets correctly, you can compare the length of the holdout set and learning set extracted from a time point CSV file, which should be equal in total to the length of the time point CSV file. Well, let's organize our time points by creating holdout and learning folders, each containing the corresponding time point CSV files. Since the option to create a folder doesn't work at the time I'm making this video, I had to do it through my File Explorer. Well, that wraps up everything for the third step of the testing phase. See you soon for the next step.